Imagine a spaceship gliding silently through the cosmos. It has no giant fuel tanks. No fiery rocket exhaust pushes it forward. It doesn't even have solar sails catching the faint light of distant stars. Instead, this ship is propelled by the very fabric of empty space itself. It moves by harnessing the energy of nothingness. This sounds like something straight out of the most imaginative science fiction, a concept so wild it seems to break the fundamental laws of physics. Yet this idea isn't just a dream from a novelist's mind. It's a tantalizing possibility, rooted in one of the strangest and most profound areas of modern science, quantum mechanics. The notion that we could travel across the vast emptiness of space using the empty space as fuel is a truly mind-bending one. For decades, we have relied on a simple principle for space travel. For every action, there is an equal and opposite reaction. We throw mass out of the back of a rocket at high speed and the rocket gets pushed forward. This is Newton's third law in its most glorious form. But this method has a major limitation. You need to carry all your fuel with you from the start. This makes spacecraft incredibly heavy, expensive, and limited in how far or fast they can go. What if there was a way to bypass this need for propellant? What if the universe provided the push for free, everywhere, all at once? This is the core promise, or perhaps the ultimate illusion, of quantum propulsion. To understand how an engine could run on empty space, we first need to completely change our idea of what empty means. For most of human history, a vacuum was the definition of nothingness. But the quantum revolution of the 20th century turned this classical idea on its head. It revealed that what we perceive as empty space is not truly empty. It is a bubbling, seething cauldron of energy and fleeting particles. This restlessness is due to something called the Heisenberg uncertainty principle. One of its many strange implications is that you can never know both the exact energy of a system and the exact amount of time it has that energy. This opens the door for energy to be borrowed from the vacuum for incredibly short moments. During these fleeting instants, pairs of virtual particles, a particle and its antiparticle, can spontaneously pop into existence from nothing. Think of the vacuum not as a calm, still pond, but as a boiling pot of water. Even though the water level appears constant from a distance, the surface is a chaotic mess of bubbles forming and bursting. The quantum vacuum is like this, but instead of water bubbles, it's pairs of virtual particles. This constant frenetic dance of particles appearing and disappearing is called quantum fluctuation. So, if the vacuum is constantly fizzing with these quantum fluctuations, what does that mean for its total energy content? It means the lowest possible energy state of any physical system, including empty space, is not zero. This is what physicists call the zero-point energy. It is the universe's fundamental background hum, an energy that can never be silenced, because it is a consequence of the laws of quantum mechanics itself. The scale of this energy is a subject of intense debate among physicists. When they try to calculate how much zero-point energy there should be in the universe, they get a number that is staggeringly, astronomically large. It's so enormous that, if it were all gravitationally active, it should have ripped the universe apart the instant it was born. This discrepancy, known as the cosmological constant problem, is one of the biggest mysteries in all of physics. Think of it like the deep, inaudible bass note from a massive sound system. You might not be able to hear the sound itself, but you can feel the vibrations in the floor and see the windows rattle. Zero-point energy is like that cosmic bass note. It's a baseline level of energy that fills all of space everywhere, from the center of the Earth to the most distant voids of the cosmos. In 1948, the Dutch physicist Hendrik Casimir made a startling prediction. He was working at Philips research labs, studying the sticky forces between molecules, when he stumbled upon a bizarre consequence of quantum vacuum energy. He proposed a simple thought experiment. Imagine placing two perfectly flat, uncharged metal plates extremely close to each other in a perfect vacuum. Classically, you would expect nothing to happen. There is no gravity, no electrical charge, no air pressure. The plates should just sit there, motionless. But Casimir realized that the quantum vacuum would behave differently inside the gap between the plates compared to outside. This difference, he calculated, would create a real physical force. Here's the beautiful logic behind it. Outside the plates, virtual particles of all possible wavelengths can pop in and out of existence, just as they do everywhere else in the universe. However, the tiny gap between the plates acts like a filter. Only virtual particles with wavelengths that fit neatly into that gap can exist there. This creates a fundamental imbalance. The greater pressure from the vacuum fluctuations on the outside of the plates pushes them together. For nearly 50 years after Hendrik Casimir made his prediction, the effect remained a theoretical curiosity. It was a ghost in the physics textbooks. Everyone agreed it should be there, but the force was so incredibly weak and the experimental conditions so demanding that no one could definitively measure it. The challenge was immense. Scientists needed to build an apparatus that could bring two surfaces within a few hundred nanometers of each other in a high vacuum, while ensuring they were perfectly parallel and free of any stray electrical charges. The breakthrough finally came in 1997. At the University of Washington, a physicist named Steve Lamoureux devised a brilliant experiment. Instead of using two parallel plates, which are notoriously difficult to align perfectly, he used a flat plate and a small sphere. He attached the sphere to an incredibly sensitive device called a torsion pendulum, which can measure minuscule twisting forces. Lamoureux's experiment was a stunning success. After carefully accounting for all other possible forces, he measured a tiny attraction between the sphere and the plate that perfectly matched the value predicted by Casimir's theory. The ghost had been caught. The experiment was hailed as a landmark achievement in physics. It provided the first direct mechanical proof that zero-point energy was real and that the quantum vacuum could exert a force on macroscopic objects. The confirmation of the Casimir effect did more than just excite physicists. It lit a fire under the imaginations of inventors, dreamers, and those searching for the ultimate technological breakthrough: free energy. The logic seemed seductively simple. The quantum vacuum contains a vast, perhaps infinite amount of energy. The Casimir effect proves we can tap this energy to create a real force. Therefore, it should be possible to build a machine that extracts this energy continuously, providing limitless power from nothing. This idea quickly became entangled with the age-old dream of perpetual motion machines. These are hypothetical devices that can do work indefinitely without an external energy source, a concept that has fascinated and honestly frustrated inventors for centuries. The internet bloomed with patents, diagrams, and bold claims of working prototypes, often hidden away in secret labs, suppressed by powerful energy corporations. The problem is that this beautiful dream runs headfirst into one of the most robust and sacred laws in all of science: the law of conservation of energy. This law, also known as the first law of thermodynamics, simply states that energy cannot be created or destroyed. It can only change from one form to another. The vacuum energy is the lowest possible energy state of the universe. It's the basement level of the universe. You can't drain water from the floor of the basement to power a turbine because the water has nowhere lower to flow. Let's dig deeper into why the dream of a free energy machine powered by the Casimir effect falls apart under scrutiny. Imagine our two metal plates again, suspended in a vacuum. As they are brought close together, the Casimir force pulls them inward, doing work. Here lies the catch, the cosmic fine print that nature always includes. To pull the plates apart, you have to fight against the very same Casimir force that pulled them together. And because of the law of conservation of energy, you will find that you have to put in at least as much energy to separate them as you got out when they came together. This is a recurring theme in physics, sometimes jokingly called the conservation of misery. You never get something for nothing. You cannot pull yourself up by your own bootstraps, and a spaceship cannot push itself forward without pushing against something else. However, this idea runs into an equally formidable obstacle: the law of conservation of momentum. This law states that for any object or system of objects, the total momentum must remain constant unless an external force is applied. Proponents argue that the spaceship is pushing against something else, the quantum vacuum. But here's the problem. The vacuum, in its ground state, is the same everywhere. It has no preferred direction. It is perfectly uniform or isotropic. Pushing against it is like trying to swim in water that has no substance. Imagine sitting inside a sealed box and trying to make it move by pushing on the inside wall. All you will do is push yourself back against the opposite wall. The box as a whole goes nowhere. Despite the immense hurdles presented by the laws of conservation, the tantalizing nature of the Casimir effect has kept a small but dedicated group of scientists working on the problem. They are not chasing perpetual motion or free energy. Instead, they are exploring the very edges of known physics. The most basic idea for a Casimir engine involves motion. Since the Casimir force changes with the distance between two surfaces, what happens if you move one of those surfaces very, very quickly? Imagine one of the plates in our classic setup is not stationary but is oscillating back and forth at an incredible speed, approaching a fraction of the speed of light. The quantum vacuum has to react to this moving boundary. The theory predicts that this rapid movement can convert some of the virtual particles into real, detectable particles, real photons of light that radiate away from the moving plate. This is known as the dynamic Casimir effect. In 2011, a team of researchers claimed the first observation of the dynamic Casimir effect using a superconducting circuit. They detected microwave photons that appeared to be generated from the vacuum, just as the theory predicted. This was a crucial first step, proving that we can, in fact, tickle the vacuum and make it spit out real particles. The dynamic Casimir effect, really opens a new door in the search for quantum propulsion. If moving a boundary can actually create real photons, and photons carry momentum, then, well, you've got the ingredients for a potential drive. The idea here is that these newly created photons would radiate away from the moving surface. According to the law of conservation of momentum, if you shoot photons out in one direction, the surface that created them must feel a recoil, a tiny push in the opposite direction. Scientists like Dr. Harold Sonny White, formerly of NASA's EagleWorks laboratories, have actually published theoretical papers exploring such concepts. They propose building resonant cavities where these effects could be amplified. By carefully tuning the size and shape of the cavity and the frequency of the oscillation, they theorize it might be possible to create a net thrust that's greater than what you'd get from just using the input energy to power a conventional photon rocket like a laser. However, this is where we step from confirmed laboratory physics into the realm of highly speculative theory. While the dynamic Casimir effect has been tentatively observed, producing a stream of photons strong enough to create a meaningful thrust is, honestly, another matter entirely. Many argue that the photons would be created in all directions, not in a nice, neat beam. This would mean the recoil forces would cancel each other out, resulting in a device that just vibrates and heats up, but ultimately goes nowhere. Even if building a real Casimir engine is, beyond our grasp, the idea serves as a powerful tool for physicists. It's a what-if machine that lets them push the boundaries of their theories in thought experiments. For instance, some physicists have explored what would happen if you could create a wormhole, a theoretical tunnel through space-time, and hold it open using Casimir energy. Another fascinating thought experiment involves the concept of a movable Casimir cavity. Just imagine our two plates are inside a box on wheels. When the plates are pulled together by the Casimir force, they do work. The overwhelming consensus is no, due to the conservation of momentum. However, designing these theoretical machines and then proving why they cannot work is an incredibly useful process. Could a sufficiently advanced civilization harness these effects? Could they create localized bubbles of modified vacuum to push a ship? This is far beyond our current capabilities, bordering on magic, but it provides a playground for theoretical physicists. By asking what if, scientists can map out the landscape of physical possibility. The Casimir engine, in this context, is less of a blueprint for a real device, and more of a philosophical probe. Where physics stops, science fiction begins. The idea of a propellantless drive that pushes against the fabric of space-time is, honestly, a beloved staple of the genre. These fictional drives are the ultimate expression of technological freedom, allowing humanity to break the chains of planetary gravity and truly explore the galaxy. These stories often feature a brilliant but misunderstood scientist who unlocks the secret, proving the stuffy, conservative scientific establishment wrong. This is a powerful and appealing narrative, as it taps into our desire for revolutionary breakthroughs that change everything overnight. However, science fiction also serves as a powerful medium for exploring the potential consequences and dangers of such technology. Some stories use the concept to explore cautionary tales. The Casimir engine and the dream of vacuum energy provide a perfect canvas for these explorations. They represent a boundary between the known and the unknown, inviting us to imagine what lies beyond. In this way, the fiction keeps the scientific dream alive, even when the hard realities of physics tell us the goal is still far, far away. While a working Casimir drive remains in the realm of science fiction for now, the research around it pushes us to the very edge of what we know about the universe. This is where science gets truly exciting. The questions raised by these concepts force physicists to re-examine their most fundamental assumptions. The laws of conservation of energy and momentum are cornerstones of physics, but science is a process of constant questioning. For example, some physicists have proposed theories involving extra dimensions of space. In these models, the vacuum energy might behave differently, and it could be possible to create an asymmetry by interacting with these hidden dimensions. The search for quantum propulsion is, in many ways, tied to the quest for a theory of everything. This is the grand ambition of physics to unite quantum mechanics, the science of the very small, with general relativity, the science of the very large and gravity, into a single, cohesive framework. In the end, even if we never build a Casimir engine, the journey of exploration is valuable in itself. The pursuit of these seemingly impossible ideas leads to new discoveries, better technologies, and a deeper understanding of our universe. The dream of harnessing the vacuum may always remain just that, a dream. But it is a dream that pushes us forward, taking us on a fascinating voyage to the absolute limits of scientific knowledge, and perhaps one day just a little bit beyond. So where does our journey leave us? Can we build spaceships powered by the endless energy of empty space? The answer, at least for now, is a clear and resounding no. The dream of a Casimir engine, a device that pushes against the quantum vacuum to achieve propulsion without propellant, remains firmly in the realm of science fiction. While the Casimir effect itself is undeniably real, a ghostly but measurable force born from the fizzing energy of the void, harnessing it for free energy or propulsion runs headfirst into the most fundamental and well-tested laws of our universe. You simply cannot extract net energy from the universe's lowest energy state, nor can you push off of a perfectly uniform sea. Despite this sober reality, the quest is far from a failure. The pursuit of these ideas is a perfect example of how science thrives on the edge of possibility. Exploring the Casimir effect has deepened our understanding of the quantum vacuum, proving that what we call nothing is in fact a dynamic and complex place. The line between science and fiction is not a wall, but a permeable membrane, with ideas flowing back and forth, each enriching the other. The Casimir engine is a perfect citizen of this borderland, a concept scientifically fascinating, technologically improbable, but imaginatively irresistible. And in the grand quest for knowledge, that makes it a destination worth visiting.